welcome everybody. It's my pleasure to introduce Erik Curiel from the Lichtenberg Group for History and Philosophy of Physics, but also our very own BHI. This is the first of a two-part series. So this one is a primer on black hole entropy.
Okay, well, thank you to Helen and Prashant and Peter for having me back again to give a talk. It's always a great pleasure. So actually, I guess I better stand over here actually, so I can click the, wait. Slideshows, the second one. Slideshows that I want? Yeah. Okay, very good. So hey, not what I wanted yet. So I'll be speaking on today on discussing some issues about black hole entropy, what it is, why we think we should attribute entropy to black holes, some foundational, conceptual, philosophical, and physical questions that attribution raises. And then next week, hopefully, if I get through everything, we will do the same for the generalized second law. So what is black hole entropy anyway? I mean, sometimes I'm tempted to say it's just this thing, you know, but that's not really useful. So I think a slightly more precise and perhaps more answer is, well, it's, you know, in geometrized natural units, it's the area of the black hole divided by 4. Now, possibly plus corrections of order h bar. Now, this is possibly true, but it's really not illuminating. It's what we want to understand, why it's a over 4 plus possible corrections. So the plan for today is I'll begin just by pointing out a few aspects of entropy in general across all physical theories that employ the concept that attribute the quantity to systems, before diving into before narrowing the focus down to black hole entropy in particular. So, and then I'll first discuss why it is we seem to think we should attribute a black hole in the first place. I'll then discuss what kind of entropy we should be attributing to it, because as I'm sure you all know, there are 1,000,001 different kinds of entropy out there in the world. One of the most important issues that has been discussed for a long time is where exactly this entropy should live, so to speak. Is it on the boundary? Are these, you know, loosely speaking, are the relevant microdegrees of freedom, limited to the boundary, or should we include the microdegrees of freedom in the interior? And I'll conclude with some musings about the problems that this all raises. So, entropy is weird. It is probably the single strangest, most, at least for me, it's the single strangest, most puzzling physical quantity in all of physics. I often find it just really deeply baffling when I try and figure out what entropy is. And what's remarkable, I mean, it has many remarkable features. One, it's I think, besides perhaps energy or mass energy, it's the most ubiquitous physical quantity. Essentially, every physical theory defines, or at least admits a definition of an entropy. I say almost. The only one I actually don't know, I don't know how to try and characterize an entropy for, interestingly enough, is Newtonian gravitational theory. And maybe the mechanics of rigid bodies and Newtonian mechanics. But everything else, you can, if you do a little bit of work, you can characterize an entropy for the system that you're working with.
So including in vacuum maxwell?
Yeah, sure, entropy is 0.
But you can define it in terms of the field strengths or...
Yeah.
Only for classical and semi-classical systems, right?
Yes, that's right. Well, I mean, in quantum mechanics, you have the von Neumann entropy, if that's what you are talking about.
But it doesn't have the same kinds of property.
No, it's
that
a-
you have in classical systems,
No, in
right?
fact,
Yeah.
no, in fact, and again, one of, well, I say every physical theory admits an entropy. And the indefinite article there is important. Because all the different kinds of entropy. I mean, sometimes it's appropriate or only possible to attribute, say, a thermodynamical entropy or a Boltzmann entropy or a Gibbs entropy or von Neumann entropy or Shannon entropy or a Rényi entropy or Salas entropy, or everyone has an entropy named after them. So you have a wide choice, and they all have different properties, and this is again one of the many mysteries to me of entropy. I mean, you can attribute energy to everything just about, but energy it's always the same. Energy is just energy, but that doesn't seem to be the case for entropy. And the really intriguing property about entropy that I'll just very briefly discuss before we narrow down to black holes is that in every single case I know of where you can attribute an entropy, and for every kind of entropy standardly used, entropy is a fundamentally modal quantity. And I'll say what I mean by that in a moment. I'm using modal in a standard philosophical sense, meaning that it has something to do with possibility or necessity, counterfactuals, something. It's not, kind of fixed, indicative, determinate property. I mean, and this, just as an aside, I can't help remarking that this fact about entropy, which is, I think, really oddly not unexamined and not discussed in neither the philosophical nor the physics literature, really makes a lot of the traditional problems about entropy become really, I think, more poignant and difficult. I mean, given that entropy is modal, it I think really becomes more difficult to talk about its relation to the area of time, to the interpretation of the second law. But possibly, really engaging with this fact about entropy, perhaps it would suggest possible new avenues of attack on these questions. But I'm not going to discuss that in this talk. So what do I mean when I say entropy is modal? Well, either the definition derives from a principle that itself is modal in character. This is the case for the characterization of entropy, the grounding of entropy in the Clausius and the Kelvin postulates in ordinary thermodynamics. Or the quantity is not an intrinsic property of a single state, but a counterfactual measure of how the state would change were it transformed into a standard reference state, Clausius entropy. Or the quantity is not an intrinsic property of a single state, but a property of a modally characterized class of states, the possible microstates compatible with the macro state, Boltzmann entropy. Or the quantity is not an intrinsic property of a single system, but is a property of a modally characterized class of systems, the Gibbs entropy, which is defined over a possible ensemble. Or a combination of these, von Neumann entropy, which actually includes elements of the modality of Boltzmann and Gibbs entropy. Again, I don't want to go into this too deeply. I just want to get a broad sketch of this. I don't know how these conditions or characters or properties of entropy, different entropies relate to each other. I'd really like to know how they do. So, Priya, this is in part one of my puzzles about how different kinds of entropy relate to each other. And intimately related to these is that entropy is the only physical quantity I know of also that mediates no physical coupling between physical systems. There's no interaction that is, kind of guided, mediated, measured by entropy. And correlatively, I think there's no such thing as an entropometer. You can't build a device that measures entropy directly. You always have to measure something else and then calculate entropy from that. Now, that's a common practice in physics. We often measure something else and calculate another quantity. But according to the physics we know, in principle, you can always build an instrument that couples directly to a physical quantity. It may be impossible in practice, but the theory tells us in principle how to do it. Not true for entropy.
There's a question in the chat. Jacob asks, is entanglement and entropy in quantum mechanics usually understood to be modal, even if one treats the wave function as a physical state?
Yeah, so on the entanglement entropy is if you like, just a variation on the von Neumann entropy and shares all of its modal properties. There's a lot to cover for black holes, So I'd be happy, I want to try and get to the black hole stuff. And if people want to come back and ask me about all this, about the different modalities and how von Neumann or entanglement entropy is modal, I'll be happy to talk about it maybe during Q&A or emails or something, or offline or something like that. Please.
So these are definitions, and so that I kind of I come also from black holes, but on the classical side, where would, for example, the Wittgenstein-Hawking type of formula entropy lie within this postulate?
That is an excellent question. So for semi-classical black holes or in the laws of classical black hole mechanics, the entropy is the area. Now, this is an intrinsic property of a single state of an individual system. No arguments are needed for a natural zero point, like with the Clausius entropy. There's no counterfactuals involved in the definition. There's nothing probabilistic about the definition. The physical significance is fixed by non-modal principles, the first law, the area law, the generalized second law. So black hole entropy is not modal, it seems, in the way that every other kind of entropy is. And there is an entropometer. You can, in principle, just get a bunch of friends together, if you know where the event horizon is, and just each of you has a little measuring device for area, and you all just go and you can accelerate right up to near the event horizon and tile the event horizon with your little area measures, and you can measure the area directly. So this already emphasizes that whatever black hole entropy is going to be, I think, quite radically different in some ways, at least, from the entropy of ordinary entropy for ordinary systems, or both classical and quantum. So why do we think there is an entropy for black holes at all? I mean, of course, there are these striking formal analogies between the laws of ordinary thermodynamics and the four laws of ordinary thermodynamics and the four laws of black hole mechanics or black hole thermodynamics. But that really doesn't seem to be enough, because, for instance, in the remarkable 1973 paper of Bardeen, Carter, and Hawking, where they first derive and list all the four black hole, the laws of black hole mechanics that we know, they explicitly argue and say, and I think they give some good reasons for it, and later people like Wald and Jacobson have also given good arguments, that this formal analogy cannot suffice for saying that this is a physical entropy. Something more is needed. And I think for a lot of people, the most initially plausible way to explain what it is that black hole entropy measures and why it is we think it's an entropy is its relation to Hawking radiation and the well-defined temperature of Hawking radiation. Because temperature and entropy in physics seem to go together like Wurst and Senf, sausage and mustard, which is a for someone who lives in Germany, that's about as natural a combination as you could possibly have. Although, as we'll see, it might be more correct to say that they go together like Sturm und Drang, but perhaps we'll see. But I actually think there's no real connection between the reasons for attributing entropy to black holes and the Hawking radiation, Hawking temperature. I mean, some kinds of entropy, like Shannon information entropy, are defined for systems that have no physical temperature. And many people think that information entropy is of really fundamental, essential importance here. In any event, Hawking radiation, as I think shown by very compelling and powerful arguments by Visser and his compatriots, not compatriots, but collaborators, one of whom may be a compatriot. Hawking radiation is strictly kinematic. You only need a Lorentz metric with an appropriate structure that to guide the quantum field in the appropriate way. It's nothing.
Also need the event horizon.
You actually don't even need a horizon. You need an appropriate kind of barrier for quantum mode, so to speak, to bounce off of, and that quantum barrier should have an appropriate kind of a momentum or angular momentum, a barrier. But you don't need an event horizon for that. Sean Hayward has characterized what he calls dynamical black holes, and Ashtekar and Fairchild and some others have characterized what they call isolated horizons. And there are good arguments for attributing and in both cases, they've derived the analogs of the 4 laws of black hole mechanics for these more generalized horizons. And everything seems to work pretty well. But in any event, one of the really beautiful things about these Visser and Barstow et al. Papers is that they actually derive a set of minimal conditions, of very general physical principles that are required to imply Hawking radiation is there. And they explicitly show you don't need an event horizon. What you need is really, the minimality of what you need is really quite striking to get a Hawking effect.
Which is what?
Basically that you need a Lorentz metric and you need the appropriate affine structure to get, if you know like Hawking's original derivation, the derivation essentially relies on a particular relation between the affine parameter on past null infinity and the affine parameter on future null infinity. And if you map one to the other by say by a null geodesic kind of tracking excited mode to the quantum field from past null infinity to future null infinity, that relation there's a kind of an exponential peeling relation, and that is what immediately leads you to the Planck distribution. And for that, you don't need the horizon. You just need the affine structure in the interior space-time to be appropriate to give rise to that exponential peeling relation.
So that's more like.
No. In fact, for Unruh, you don't need the peeling. You don't need the exponential peeling. I actually think this is a somewhat controversial claim, but I actually think the Unruh effect is really quite different from the Hawking effect. That discussion, that discussion would take us far afield. But Hawking radiation is strictly kinematic, but entropy is fundamentally dynamic. That we identify it with 1/4 of the area depends sensitively on the form of the Einstein field equation. In alternate theories of gravity, the coefficient 1/4 is different when you have different field equations. So entropy really is dynamic.
Another question. So Elon asks, we seem to observe area loss cases across many other systems though, in particular for vacuum states of QFT and kindness matter systems, where the entropy also scales with the area. So arguably, we could go and also measure it by measuring the area. Would that mean that actually there is an element of non-modality in that definition of entropy as well?
That's an excellent question. And I would say, I personally would say that in that case, although the area of say the quantum field is proportional to the area, that's not the entropy. The entropy is still the von Neumann entropy. And the fact that you can measure it by measuring area is analogous to the fact that you can measure the entropy of a cloud of gas by measuring its energy and its volume, or something like that. So I would still say that even in this case, it's modal, but that's certainly, I think, a fair point to discuss further. So Bekenstein's original motivation for attributing entropy was to save the second law. And to do that, you also have to invoke the first law. But this still seems to me to be the best argument for attributing entropy to a black hole. But we'll talk about this next week when we talk about the GSL. I just wanted to give you a very quick overview of why it is we feel the need to attribute entropy to black holes. So what kind of entropy are we attributing when we attribute entropy to black holes? Well, the most popular, common, influential attributions of entropy are thermodynamical, by which I mean phenomenological or Clausius, Boltzmann, Gibbs, von Neumann, which I include entanglement entropy under, Shannon or information entropy, graphic entropy, or something else entirely. I'll have one remark to make about the something else entirely at the end of this section. So I claim, I'll now discuss the elements of that list. I claim that there had better be at least a good thermodynamical conception of black hole entropy. Because if you think about how it is, if you think about the evidential support that we have for statistical mechanics in just quite generally, not in black holes, but in condensed matter, in fluid dynamics, for black body radiation, it's always the case that how we gather evidence for the statistical mechanical properties of a system, 99% of the time is actually by using thermodynamics. It's very, very rare for us to really latch on to the statistical fluctuations and use that directly as an evidential basis for claims in statistical mechanics. Thermodynamics is what makes us think that these systems have micro degrees of freedom, that that the thermodynamic quantities are derived from based on statistical averaging, appropriate statistical manipulation of the statistics of microdynamics of states. So I think that at least if we want to follow anything like standard evidential practice in physics, in this case, we really need to believe that there is a sense in which the entropy of black holes is thermodynamical in order to give us evidence that it's fruitful to look for an underlying, I can't say that word, a statistical mechanics of an underlying set of microstates, micro degrees of freedom, and their microdynamics. This is a somewhat controversial claim, or perhaps a slightly hysterical claim, but y'all should be used to that by now for me. String theory, loop quantum gravity, all the other programs in quantum gravity, they can count all the microstates they want. But we need independent reason they're counting physically relevant microstates, that they're latching on to the right physical micro degrees of freedom. And that, I think, the independent reason can come only from a belief that what we're dealing with is a thermodynamical entropy.
By linking it to thermodynamical, you're already taking sort of Boltzmann's approach, right? Because all the other definitions rely on micro states, or
so that's a really good question. So I would say Boltzmann and von Neumann depend manifestly immediately on microstates. Gibbs does so in a slightly more subtle way, because while the probability distribution is over a set of probably macro systems, over an ensemble of macro systems, the energy levels that you use in constructing the distribution function, the partition function, comes presumably from some idea about the microstates. But there is a sense also in which Gibbs is precisely the entropy where one needs to know the least, so to speak, about the microstates. And I'll actually come back to that in a moment when I talk about Gibbs.
I mean, it seems to me that some of the people who work on this say if you can get A over 4, if you get the factor of 4, ipso facto, you're looking at the right thing. So they proceed in the other direction.
They do. And I will have something to say about that later on in the talk.
It's kind of interesting because even if you go, because you were mentioning other theories, that within general relativity, if you go to higher dimensions of space-time, you still get that 4.
No, it's simply the same part.
Right.
Yeah.
Independent of the dimension.
Yeah, which is truly amazing. That's truly remarkable.
There's something.
Yeah.
The property.
I'd like to understand that.
So would I.
Okay.
No, please.
I think I have a question. So you mentioned earlier that you wanted to take so if you have in the information theory setup, you count entropy by looking at the different information that you have. That's not really thermodynamical in nature intrinsically, right?
No, it's not.
So here, is there a connection that can be made without with black hole entropy and some sort of information entropy without actually needing it to be a thermodynamical quantity?
Again, so I think if we don't have thermodynamics, we don't have any reason to attribute any other kind of entropy to it at all. But the case of information entropy is really difficult. I think I really understand, or insofar as I understand anything about entropy, I think I understand Shannon entropy when it's applied in its original context, when there really is something that one can think of as a communication channel, when there's a sender, when there's a receiver, when there's a well-defined kind of a structure and set of possible messages, then I understand information entropy. But since one never has anything really like that when you try to apply information theoretic ideas in other places, I quickly begin to lose my grip on what it means. But that's something that's I think something else really important to talk about, because so many people think that information theoretic notions of entropy are the right ones to use in this context. So so what do we have in favor of thermodynamical entropy? Well, we have the GSL. We have the fact that semi-classical black holes support construction of Carnot-like cycles. That actually goes back at least to the early 90s, but there's been a lot of later work on it. And then there are some speculative, perhaps crazy arguments that classical black holes plus strictly classical matter jointly have well-defined thermodynamics. Besides the author of that paper, there actually are a few other folks who like it. Ted Jacobson and Carlo Rovelli tell me that they really like it. Bob Walt hates it. Unruh, I can never get an answer out of Unruh. He always deflects. But so a few folks do like it, including from time to time the author of the paper, but even the author of the paper doesn't always buy it. So there are plenty of grounds for questioning and criticizing these last two considerations in favor of attributing a thermodynamical entropy, but in the interest of trying to discuss all the different forms of entropy, or many of them, I'll leave. I won't go into detail about that. Feel free to ask me during Q&A.
Is the argument of three, just
Yeah.
to state the case, not to make the argument for
Yeah.
it, that classical black holes might not have a well-defined entropy, but with classical matter, then together they do. Is that the idea?
No, I would say that classical black holes, my argument is that classical black holes do have a well-defined thermodynamical theory, contra a lot of orthodoxy. And the argument for showing this, so I would say black holes by themselves, areas with the entropy, even in a vacuum, area will increase if there's gravitational radiation around. But the argument, at least that I use, which is a construction of a Carnot-like cycle, does depend on the presence of some other matter floating around. But we want statistical mechanics, because thermodynamics we think is an effective, emergent, higher level theory. We want an entropy that somehow reflects something that is captured by statistical mechanics. And classical GR, not even semi-classical gravity, neither one alone can provide a statistical construction, because in semi-classical gravity still treats the black hole as an entity defined entirely by the classical spacetime geometry. There's no way to describe a black hole by physical attributes arising as gross statistical measures over more finely grained degrees of freedom. So any statistical accounting must come from a theory that attributes to classical geometry itself a description based on some appropriate microstructure, which presumably will be quantum in nature, underlying a classical description of the space-time structure of the black hole.
Erik, I have a question on this. So when you say area, right, it's a quasi-local quantity that you define on the horizon. Now, what is the argument against saying that all the different interior solutions to the same, which give you the same area, all of them could constitute different microstates, and which you can then count and say that this is the way that we define the area itself from the exterior. So would that work? Or
well, so that I'm going to discuss that in the inner versus outer section immediately after this. You guys are doing great. I mean, you're asking all the right, well, what I think are all the right questions. This is great. So a surprisingly common argument for attributing a Boltzmann type entropy to black holes goes something like this. And I think exemplars are these two papers by Sorkin and Preskel that I cite. So, Planck length plus a distinguished geometry provides a natural coarse graining. You just tile the event horizon with a Planck area, squares. And the horizon then, you then assume that the horizon carries some kind of information about that the dynamical states, the dynamical quantities are characterized by an information, in each Planck tile, there's some micro quantity defined, and that the density of this information is approximately 1 bit per unit area. And then it's just a simple combinatorial argument. The total number of configurations is of the order of 2 raised to the power of the area, which is which and the log of that total number is the area times log 2. So you're really, really in the ballpark. This is basically getting to Bekenstein entropy. Voila. Now, the virtues of this kind of argument is that it makes absolutely minimal physical assumptions, at least compared to other kinds of arguments in this general area. And it's largely independent of the details of any theory of quantum gravity. It really just makes very, very general assumptions, seemingly very minimal and quite, in some sense, plausible assumptions. Nonetheless, I think it's a crappy argument. If you really are going to talk about bits and information, I want to know what the yes/no question is. That's a somewhat ad hominem argument, which you may not take very seriously, but I actually think is a somewhat serious question. In any event, you seem to be facing a dilemma here. You're either counting microstates, you're either not counting microstates that are relevant to dynamics in any straightforward and appropriate and relevant way, or else you're making what I think is a very strong and unwarranted assumption that the fundamental degrees of freedom are binary or at least strictly and uniformly bounded by a very small number to get the something like the right coefficient for the log n, for the log of the coefficient, for the log of the number of configurations. And if you do make this assumption, then you are also forced to make what I think is the strong and unwarranted assumption that such degrees of freedom can couple in the right way with a higher order levels of degrees of freedom of ordinary quantum fields, because presumably these degrees of freedom that you're attributing to the Planck tiles are at least possibly effective degrees of freedom of some deeper underlying theory of quantum gravity, or they might even be the degrees of freedom of a full theory of quantum gravity. But in any event, in order to get black hole thermodynamics to work, you have to get these really deep fundamental level degrees of freedom to couple to really high level, relatively speaking, low energy degrees of freedom of ordinary quantum fields. And I don't see how physically that's supposed to work. And I think that this is related to a similar problem in page time calculations, but don't have time to go into that. And I have similar problems with many Boltzmannian state counting arguments in weak regime quantum gravity calculations. The string theory calculation where the degrees of freedom are self-intersections of d-branes, or in loop quantum gravity, you have an ensemble or superposition of event horizon states, and causal set theory, you have causal links crossing the event horizon, and so on. And I think, again, that they beg the question by assuming that they are counting the dynamically relevant states, and also that counting measure, which is what they have to use, is the appropriate measure. But counting measure is almost never correct in statistical mechanics. At the very least, you always need some kind of weighting. And it's not clear how that's supposed to work in these cases. And again, Peter, I'll return to your question, which I think is a very important question, about the fact that Strominger and Voppa and Ravelli and Du and Sorkin would all say, but look, we're getting the right answer. That's evidence that we're counting the right microstates. So Gibbs. I actually know of no argument for or against Gibbs entropy in the literature, which is I find somewhat odd. But I actually think that Gibbs is really probably the most appropriate form of entropy to use for black holes in the semi-classical regime. Number one, I think really importantly, almost all proofs of the GSL use Gibbs. The only one I know that doesn't is for a very specific model in 2D string theory, and so I'm really not impressed. The Gibbsian statistical mechanics is exactly what one wants and what one in fact needs to use when one has no secure knowledge about the microstructure, about what the character of the microdegrees of freedom and their dynamics. Gibbs allows you to give a statistical mechanics of a system almost completely agnostic about the microstructure. And I claim in our current epistemic state where we really don't know what the microstructure of gravitational systems are, the quantum microstructure of gravitational systems are. Gibbs seems to me to be a really nice way to kind of work as safely as possible, so to speak. And it also avoids, and again, for the same reason, it avoids the Boltzmann worries about latching onto the right physical microdegrees of freedom and dynamics.
Sorry, so on this, when you define the ensemble, could you not translate the ensemble, how you define it, as some sort of fluctuations of like the event horizon, like the geometry of the event horizon, or just say like it's area increasing and decreasing. If you do that, then you can then translate that to the variation, the tiles, the Planckian tiles. So is there not a way to translate these sorts of things in some appropriate way to?
So I would say that it's relatively easy to move from Boltzmann to Gibbs for exactly the kinds of reasons you're suggesting. But because in Gibbs, as I suggested earlier, the only knowledge you need about the microstructure is some idea about what the discrete distances are in the distribution of distances in the energy spectrum. And you can give kind of good physical guesses about that. The distances are going to be some function of h bar, increasing as energy levels increase, without saying anything about what gives rise to that energy spectrum.
But that sounds like fixing indirectly the log factor, right? Because you're saying that there's a spacing, and that's giving you some indirect measure of the number of degrees of freedom that you have in each Planck tile.
Yeah, but it doesn't say anything at all about what those microdegrees of freedom may be, or what theory they come from, or whether they're associated with Planck tiles. They don't have to be associated with Planck tiles. So it's completely agnostic about how that energy spectrum comes about. So entanglement entropy. Essentially, the entanglement entropy, the idea is originally due to Sorkin, is that black hole entropy is proportional to an accounting of cross-horizon quantum field entanglement correlations. Now, the virtues of this is one, that it allows you to derive the semi-classical Einstein field equation, as Ted Jacobson showed. I think it's really a remarkable and beautiful argument. The demerits of entanglement entropy is the species problem. If the more quantum fields you have, the larger the entanglement entropy is going to be, and so I don't see any reason a priori why you'll end up with the 1/4 factor. It will be, if you believe that for one quantum field it'll be the entanglement entropy will be proportional to area, you have good reason to believe that it'll be proportional to area for all quantum fields. But then if there are a bunch of quantum fields, it's each one contributing, it's difficult to see how you're going to get 1/4. I think that problem might be solved by just saying that's just order h bar corrections. Let's not worry about it. To me, a more important kind of conceptual question is I really don't see how entanglement entropy can explain increase in entropy when a classical entropic object falls into a black hole. You throw in Wheeler's infamous hot cup of tea. How can entanglement correlations of quantum fields across the horizon be sensitive in the right way to the classical cup's mass and only its mass? And there's absolutely no reason I can see for this accounting of entanglement correlations to show up at the classical level in the area theorem which remember is in classical GR is a theorem of pure differential geometry. And it may be the case that as area increases, then entanglement entropy increases. But I don't see any reason to suspect the converse, that as entanglement entropy increases, the area increases. But it's that direction that really matters. And in any event, entanglement itself has really deep and unresolved conceptual issues. There's a really beautiful paper by John Ehrman about that.
Sorry.
Mhm.
So if you take Einstein coupled minimally to some other fields, say a scalar field, electromagnetic, etc., you always get, so the first question is, do you always get this 1/4 factor independent of how many fields there are? Just classically, if you would try to calculate the entropy of the black hole that you get.
You do.
So-
That comes from the coefficients in the first law.
Right. So here you're making a very interesting different argument. You're saying that if you were to count it like this, if you add more fields, you would expect that to not be A/4, but like times some factor.
Right.
I see this.
But wouldn't it be the case? I don't know, but like maybe if we add like other fields within the area itself of the black hole, like change, like for instance, if we have like E and M instead of like having Schwarzschild black hole, would have like a Reisman black hole. Maybe has like more area.
Well, let's think about, let's say you have a scalar field that, you know, with a given stress energy distribution, and you use its entanglement entropy to say, you know, you say, look, its entanglement entropy is proportional to the area, and if you close your eyes and or squint your eyes and wave your hands a bit, you can get 1/4, the 1/4 coefficient. But now let's say that I have a scalar field and a Maxwell, and a Maxwell field, and jointly they have the same numerical values for the stress energy distribution. Well, you're going to get the same mass with a black hole, but you're going to double the correlations across the event horizon. So, crudely speaking. Holographic entropy. Again, I'm not going to give you a detailed explication of what it means, because this is not that kind of talk. Just very crudely, the holographic entropy is what one can calculate, is what one can derive in spacetimes in which the holographic principle can be more or less readily implemented, most often and most famously in ADS-CFT. But more generally, whether you're in ADS-CFT or not, whether you just have some appropriate holographic principle floating around, you can say that the area of an area of privileged or null space-like surfaces in the bulk are proportional to the von Neumann entropy of, say, a conformal field theory on the boundary. Now, the virtues of this is that it's cool and exciting. The demerits are that there are compelling derivations, at least I think compelling derivations, only in non-physical spacetimes, basically those with ADS boundary conditions. And holography has even less epistemic warrant than most things in semi-classical gravity. I mean, I think it's not just okay, but it's important to speculate, to construct possible, to construct new alternatives, to construct new possibilities, and explore them theoretically. But I think it's also important to keep track of how close what you're doing is to physics that we are somewhat secure about, that we have some epistemic security about. And to my mind, I mean, a lot of semi-classical gravity, no matter what formulation you use, is pretty far from physics that we have really secure epistemic warrant for. But I think holography, even in this area, holography, I think, is further away from well-established physics than other formulations of semi-classical gravity. No, there's something else entirely. I just put this up here for sake of completeness. I'm not going to discuss any of them. If you want like references, email me and I can send you references. I forgot to add references on this slide. So, there are these exotica that are championed by small but vocal minorities: Barrow entropy, Kaniadakis entropy, Renyi entropy, Sharma Mittal entropy, Tallis entropy. But I'm not going to talk about them. So, to get to Prashant's question, So I'm clearly approaching the end of the talk time, but I'm hoping since there were a lot of questions and discussion during the talk, it'll be okay for me to continue. And I suspect I might have to use a few minutes next week to conclude this. So where does black hole entropy live? On the horizon or inside the black hole? In particular, does black hole entropy have something to do with the state or dynamics of anything in the interior? So which is perhaps another way of rephrasing, or at least formulating a question that's really, really close, importantly close to why is black hole entropy proportional to area and not as for almost all other physical systems. There should be an almost all there, because the person who asked the question about area scaling laws in other systems is absolutely right. So there should be an almost there. For almost other types of physical systems, it's proportional to volume. And I think how one answers this question has clear and sharp relevance for how one will formulate and try to prove the GSL. And I really want to give a shout out to this really extraordinary and beautiful paper from 2005 by Ted Jacobson, Donald Maroth, and Carlo Rovelli. It's written in the form of a dialogue among the three of them about whether black hole entropy should be thought of as inside or out. It's a beautiful paper. If you haven't looked at it, like, drop everything, go read it. So general considerations in favor of outside. The most natural explanation of the area law is that S lives on the horizon. The no-hair theorems very strongly suggest that the horizon itself is the dissipative part of a black hole, so to speak, the thermodynamical part of a black hole. And also the no-hair theorem suggests, as I'll elaborate on further, that it's the horizon that's in equilibrium. And the one-way character of the horizons affords relatively direct proofs of entropy non-decrease for coarse-grained dynamics, as we'll discuss next week, I hope. So those are the general considerations. Some standard arguments for outside, for entropy living on the horizon, so to speak, is that, first of all, the interior of a black hole can be arbitrarily large.
I missed what you said about area versus volume.
Oh, so that one consideration in favor of saying entropy lives outside on the boundary is oh wait, what was I saying about that? Huh. Where did I say that? Ah.
Yeah.
So it's just a question. Why is the black hole entropy proportional to the area and not, as for almost all other types of physical systems, to the volume? So standard arguments, the interior of a black hole can be arbitrarily large, just glue an FLRW into the inside of Schwarzschild. So you can have unbounded interior microstates.
Yeah, is this be a solution to everything?
Oh yeah. It violates energy conditions, but who cares? Quantum fields violate energy conditions all the time.
You can even have Kandowski sets, which does not violate any energy.
No, but when you do the gluing at the transition, you'll violate an energy condition.
On the horizon?
No, inside in the interior.
Okay.
You'll have to, because otherwise, because the singularity theorems tell you that if energy conditions aren't violated, you get a singularity.
You want it to be.
Yeah. So another argument is, look, the interior of the black hole is totally out of equilibrium. But the black hole first law, which is used to calculate the entropy, the 1/4 coefficient, is appropriate only for systems in equilibrium. And entropy, we think, counts microstates that contribute to an equilibrium macroscopic state. And only the event horizon is in equilibrium. On a related point, the dynamics of the interior are essentially one way, so it's really hard to see how you can get anything like ergodicity, which is used in almost all discussions of entropy and the second law, and just in statistical mechanics. And if you assume that the Hawking effect is unitary, at least quite close, just quite close up to evaporation, which seems quite plausible, no matter what you think
I
about
mean, doesn't,
whether it's unitary, all the way through.
on one, I mean, doesn't holography militate against number one?
Oh, there are a lot of, not just holography does absolutely. A lot of things militate against number one. Number one is not physically plausible, I don't think. But it's something, but it's an argument that people trot out to say, look, at least in principle, you need to explain why it is that the A over 4 is the right entropy, completely ignoring all features of the interior, because you can have these crazy interiors. So just as a calculational and computational conceptual fact, that seems hard to understand. So assume the Hawking effect is, so last argument in favor for outside. Assume Hawking effect is unitary, at least until close to evaporation. You can be agnostic about what happens near the end. Then Hawking radiation is correlated. Hawking radiation is always correlated with interior degrees of freedom. So the number of interior states must remain large enough to store those correlations. But if X hypothesis, ignoring number one, the interior is normal, then then the interior states decrease much faster than A near the end. So entropy better not count interior states, or you'll end up getting the wrong answer. And that's also related to some issues about the page time problem. But these arguments themselves raise puzzles that perhaps favoring the inside view. So Bekenstein entropy is smaller than the accounting of all microstates associated with a black hole, because it's A plus the interior. So how is the statistical mechanical if it disagrees with a thermodynamical entropy? How does the event horizon keep a record, so to speak, of the entropy mass energy of all matter that passes through it? Because without assuming exotic physics and low energy regimes, like the firewall paradox may seem to suggest. And how can a derivation of the second law, ignore all of that? So I think these are considerations, and I mean, I actually left one out, probably the single most important one, which should have been number one, and which is the one that Don Merolf in the paper I mentioned, that he wrote with Ted and Carlo, that Merolf really pushes, which is, look, if we just think of a black hole as a quantum mechanical system, which we should, if we think of, the world is essentially quantum at bottom, then we should be able to apply something like ordinary statistical mechanics to it. And to do that, we need to keep account of the structure, the content of all the states of the black hole, and that includes information about the interior. So I should have had that argument as well. A question?
Isn't it thought that the area contains information, but like the fact that the A over 4 is accountable for the microstates that live in there?
That's what a lot of people want to argue, but I find a lot of those arguments questionable. I mean, and this is not. I mean, it's partly a matter of taste, but it's partly a matter of. And when I say that, I mean, what is it that one demands to have an argument that one finds compelling in this area of physics, where we have no empirical evidence whatsoever to guide theorizing? And so I find a lot of these arguments, for my taste, for my comfort level, go too far beyond what I think we have somewhat secure knowledge about, or somewhat secure ideas about, or what seems too speculative, too far away. But that really is, that's to some degree a matter of taste and one's comfort level about how far away from established physics one is allowed to go. So that's probably not a very satisfying answer.
I guess I was like thinking of like something like Schrodinger alpha, where like the only kind of like possible kind that we have of the microstates of a black hole.
I mean,
the count of the microstates have always produced like the A over 4.
The Schrodinger-Alpha case is a really interesting case. It's when you really try and figure out the structure of the argument, because their paper is very elliptical. You really have to do a lot of reconstruction to pull out what the full argument is. And when you do that, you see that the argument basically that there's this kind of it's not an argument that's straightforwardly just counting intersection, D-brane self-intersections like I suggested earlier. There actually is an argument that relates calculations in supergravity to arguments in statistical mechanics of supergravity, to arguments about statistical mechanics of D-branes, to arguments about counting self-intersections of D-branes. And so you really, how comfortable you are with going through that entire stage of identifications depends on how comfortable you are with this calculation and with thinking that what they're doing is latching on to the right microstates. Some people really love it, and and I'm not saying they're wrong. I'm just saying it makes me a bit uncomfortable. And I'm not just, I mean, I have reasons. I like principled reasons why, and it's not just that I have a bad feeling in my stomach, when I read the Strominger-Vafa paper. Although I also do have the bad feeling in my stomach when I read the Strominger-Vafa paper.
For other reasons.
For other reasons. And so, in the last 2 minutes, I will just list the questions that I think the conceptual, philosophical, foundational, physical questions that I think this discussion raises. And
I think there's one question for the Q&A.
oh, please.
Because we're running out of time.
Yeah,
maybe
no,
we
please.
do this.
Yeah.
So Elon asks, indeed the condensed matter and quantum field theory states that have area entropy law scaling are just a class among many others of systems that have other scalings, such as volume. However, black holes seem to represent a general trend for gravitational systems, further confirmed by the holographic principle a la Busso, where the scaling seems to be for any gravitational system, then defined in terms of the area of light sheets instead of hyperspatial surfaces. Thus, from that point of view, the question above was misleading, and the analogy between black holes and QFT or quantum condensed matter system seems circumstantial. Yeah.
Okay, so yeah, that's a really nice question. I would say that yeah. Oh, I mean, I think it's a nice comment, and I'm quite sympathetic to it. I think balk at the claim that the holographic principle provides any confirmatory support, but putting that aside, I think I have sympathy with that for what it's worth. So, because we're out of time, I will just list the questions that I was planning to go on to discuss in a little more detail. And I'll spend the first 6-7 minutes next week discussing not all of them, because that will take more than 6 or 7 minutes, but just a few select ones. But the questions are, and there are many different entropies one can attribute to a black hole, and not just the ones I've listed, but there are many more entropic-like quantities. It turns out to be apparently somewhat important in various contexts to calculate relative entropies, to calculate what are they called? Conditional entropies. So, I mean, do we have to pick the one and true black hole entropy, and what would that even mean, and why? I mean, why? What? How do we interpret the entropy? Is it supposed to be a subjective or objective? This is a standard debate in foundations of statistical mechanics and thermodynamics. Is entropy subjective or objective? But another question that arises specifically in this context is the identity claim. Black hole entropy just is physical entropy, just is ordinary entropy. What do we mean by the same in this context, and what are the criteria that we can have for arguing for sameness, and are they reasonable? So there are many disanalogies. Some of them I've already sketched. There are several more that I want to talk about with ordinary entropy. Is this a virtue or demerit? A/4 seems to, at least in standard black hole models, seems to require prescience to calculate the event horizon, on a space like SICE, to locate the event horizon. You need to know the entire future evolution of the system. That means that S and entropy for the black hole is not a well-defined state function on space. and the enormity and discontinuity of A over 4. You know, when something collapses, you know, when a cloud of dust, when a star collapses, when the event horizon forms, the entropy jumps discontinuously by an enormous amount. For a cloud of hydrogen gas of 1 solar mass, the jump is about 10 to the 20. What, why, and how?
I have questions about 4 and 5. Before, like the area of the event, can you just like on a spatial slide, like identify the event horizon, for instance, is like the point where like given factors kind of like
No, because that can happen on other, depending on the dynamics of both the wild tensor and the Ricci tensor, that can happen for horizons that aren't the event horizon, or surfaces that aren't the event horizon.
And for 5, you know, like you mean if we have like some hydrogen contained in an area that collapses?
Yeah, let's just say you have a star that collapses. You have a cloud of hydrogen gas of 1 solar mass and it collapses.
But like where is it, like at any point like a given region has the area, if it has like a black hole, it has the entropy equal to A over 4, and if it doesn't, it has less entropy.
So before the event horizon forms, presumably the entropy of the hydrogen is just the ordinary, whatever your ordinary physical entropy you want to talk about is. Let's say Boltzmann.
Would that like stay with the volume?
Yes, it does. But as soon as the event horizon forms, the value of the entropy jumps by about 10 to the 20 and becomes proportional to the area.
The area would be bigger than the volume in this case? Like when
the entropy, the area is bigger than the entropy of the gas, which is proportional to the volume. And then as soon as the event horizon forms, you get this enormous and discontinuous jump. Why are there no significant results about any of this in algebraic quantum field theory and curved space-time? This is arguably the single most important and epistemically secure framework we have for semi-classical gravity. But there are essentially no calculations of entropy or derivations of area law or anything like this in the framework. I find that really weird. Why demand statistical mechanical calculations that rely on quantum gravitational degrees of freedom rather than something else? That's a little more complicated. I wouldn't be able to explain it here. If we get to it next week, you might enjoy it. Peter's question from earlier. All quantum programs derive A over 4. Does this trivialize the evidential power of the derivations? Or if you like, I call this the I'm always right problem. Because if they all get it right, if they all get the same number, then that strongly suggests that actually that this number really has nothing to do with the character and the properties of any theory of quantum gravity. And so then it becomes very difficult to see how it can provide evidential support for any individual theory of quantum gravity.
Yeah. I don't know if I believe that.
Mhm.
I mean, sometimes there are very different derivations that give you the same result.
Mhm.
That doesn't prove that it has nothing to do with the different theories that get you there.
Mhm.
It shows that there's something that's deep, that's
Mhm.
enacted or instantiated in the different ways of calculating.
Sure, but at least in all the cases where that kind of thing happens that I can think of in quote unquote ordinary physics, you're not dealing with radically different theories that purport to be competitors with one another as to which one is actually right about the real world. You generally are dealing with different frameworks or formulations of the same theory, and doing the calculation within that shared framework. So unless you have an example where what I'm describing in quantum gravity happens, I'm going to disagree with you on that.
Okay, let me think of some
Okay.
other examples,
Mhm.
but they're certainly there are cases where different theories give the same results. They seem to be on fundamentally Heisenberg and Schrödinger.
Mhm.
They seem to be completely different ontologies, different ways of calculating, different ways of handling time.
Mhm.
And then they give the same result. And then
Mhm.
eventually somebody realizes you just move the back end of the kettle a little bit and it's all okay. They're really the same thing. But
Yeah.
but I don't know whether I don't know enough about loop gravity to say what relationship it might have to string theory, but it seems to me that, yeah, I mean, if they gave the same results across a broad range of phenomena, I'd say there's some deep principle that goes back and forth between them, but I wouldn't say it has nothing to do with the theories.
Nothing you do may be too strong, I'll admit that. But but with the Schrodinger Heisenberg case, I would say absolutely until von Neumann, was it von Neumann or was it Schrodinger? It was Schrodinger who proved that they were equivalent. Until that point, I absolutely agree. They were in basically the same kind of situation. But as soon as Schrodinger proved that they were equivalent, then we're in the situation that I was describing for other physical theories. But I think you're absolutely right. It actually is a dream of at least some people to try to show that these different programs of quantum gravity really are related to each other in a very intimate and strong way. Maybe not exactly equivalent like Schrodinger and Heisenberg, but something close enough that we can say evidence for one is evidence for the other. And then I think we would be back on the ground where all the derivations of A/4 would be confirmatory. But until that happens, I'm cautious, let me say. So I'm already over time, so I'll leave it there and we'll pick up next week. Thank you.
Thank you, Eric.
Can I ask you this?
Like, yeah, thanks everyone on Zoom.
Yes.